so this is problem number 4 from AP Calculus AB for your response section. I'll give you a moment to pause the video and read the problem. Okay, so part A says on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. So the differential equation is right here. So in order to be able to draw that slope field, it's basically a plug and chug where I'm plugging in points and I'm getting back slopes by doing 2x minus y. So the 6 points they indicate, I'll go ahead and write down. That would be 0, 1, 0, 2, 1, 1, 1, 2, 0, negative 1, and 1, negative 1. That is a 1. So when I plug these things in, it's just a matter of doing 2 times the x value and subtracting the y value. So when I plug in 0, 1, I'm going to get negative 1. When I plug in 0, 2, I'm going to get negative 2. When I plug in 1, 1, I'm going to get 2 minus 1, which is 1. When I plug in 1, 2, I'm going to get 0. When I plug in 0, negative 1, I'm going to get positive 1. And when I plug in 1, negative 1, I'm going to get 3. So I'm going to take these slopes and I'm going to plot them at the indicated points. So 0, negative 1, that would be 1. At 1, negative 1, that's 3. So it's deeper by a good bit. 1, 2 is 0. 1, 1 is 1. 45-degree angle. 0, 2 is negative 2. And 0, 1 is negative 1. And that's part A. Part B says to find the second derivative in terms of x and y. So in order to find the second derivative of this thing, it's an implicit differentiation problem because I have x's and y's mixed together. So I'm going to go ahead and rewrite the y as f of x. When I take the derivative of this thing with respect to x, the derivative of the derivative is the second derivative. That's why the Leibniz notation comes out with this sort of funky square notation. And then on this right-hand side, the derivative of 2x with respect to x would be 2 times technically the derivative of x with respect to x, but that's just 1, minus the derivative of f of x with respect to x, which is f prime of x, which is dy dx. Now I could have written f prime there. I'm going back to the Leibniz notation here. Now, we would be done here if the problem didn't say find it in terms of x and y. I don't have x and y here, I have dy dx. So I need to make another substitution to get this in terms of only x and y. So you do have to pay attention to that when the AP exam is asking. So the way I fix that is I look back at my original statement of the problem, which is that dy dx equals 2x minus y. So this would be 2 minus dy dx, which is 2x minus y. So when I do that subtraction, it's 2 minus 2x plus y. I could have left it in the form where I didn't simplify, and that would have been just fine. That's the first part of part B. Then it says determine the concavity of all solution curves for the given differential equation in quadrant 2. So when I'm determining concavity, I'm looking at the second derivative, and the second derivative is positivity or negativity. Well, if you look in quadrant 2, all the x values are negative, and all the y values are positive. So if you're looking at this differential equation down here, the second derivative is 2 minus 2 times a negative number plus a positive number. So this is basically a positive number plus a positive number plus a positive number. So this is going to be positive, which means that the solution curve in quadrant 2 is going to be concave up because the second derivative is greater than 0. And I would need to have some sort of explanation about why the x's are what and y's are what they are in that quadrant, but this is sufficient for that explanation. So part C. Part C says let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. So this is a particular curve that passes through the point 2, 3. And then it says, does f have a relative minimum, relative maximum, or neither at x equals 2? So you know when we're dealing with relative extrema, we need to know what's happening with the derivative, first of all. So I'm going to look at the value of the derivative at the point 2, 3. So when I do that, I plug that into the actual dy dx. I get 2 times 2, right, because that's the x value, minus the y value, which is 3. So that's 4 minus 3, which is 1. So the problem says, does f have a relative minimum or relative maximum or neither at x equals 2? Well, remember, one of the ways that a function can have a relative extremum is if the derivative is 0 or undefined at that point. It's impossible to have a relative max or min without having the derivative be 0 or undefined. So this is neither, because the derivative at that point equals 1 and is not 0 or undefined. In other words, this isn't a critical point, because that's what the definition of a critical point is, right? All right. So for part D, the problem asks to find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So remember, when something is a solution to a differential equation, you can actually plug it into the differential equation and make it work. So remember, when we say dy dx equals 2x minus y, we're basically saying when we take the derivative of a function, it equals 2x minus that function itself. And they told us that y equals mx plus b is a solution to this thing. So I'm going to take the derivative of this. And remember, m and b are constants. They tell you that in the problem. So the derivative of mx would be m, and the derivative of b would be 0. Now I'm going to plug this information into the differential equation. So dy dx would be m equals 2x minus y, which is the function itself, which will be mx plus b. So I'm going to distribute that negative. And then I'm going to get everything on the same side. And combine like terms. So the x's have coefficients of 2 and n, so I'm going to subtract those. And then the minus b and minus m is like one constant, where I'm subtracting b plus m like this. Now, this next step requires something that you actually know from Algebra 1 and Algebra 2, but you don't think about very much, and that is, if you have two polynomials that are equal to each other, corresponding degree terms have to equal each other. So if you look at this thing, I have a 2 minus m times x here on one side, and no x term on the other. So for these two things to equal each other, the 2 minus m, that's the coefficient of the x, has to equal the coefficient of the x on the other side, which if there's not one, it's 0. And the same thing has to be true with the constant terms. The constant term, which is negative b plus m, would have to equal the constant term on the other side, the equal sign, which is 0. Now, if I solve this first equation, that basically tells me that m is 2. And if I solve the second equation by plugging 2m for the m, I get that b is negative 2. So those are the values of the constants. And that's problem number 4.